So thinking about the real-life large-scale social networks, the real-life social network, actually the scale of the social network is very large, with some features of for example, like the specialization in connections. Example is like a Twitter and the Facebook, and also the emergence of the dominant intermediaries with a huge brokerage rent, such as Amazon's. And the economic theory of networks offer insights on how these networks are formed and how they affect the people's behavior and also the outcomes in society. And looking at the experimental literatures, the typical experiments in the literatures are with very small group of people, ranging, let's say, 4 to 12 people. And so that in this sense, there is a gap between the large-scale network we observe in the real world and the size of the groups in the lab experiment. And the typical findings in the laboratory experiment are that the exact predictions of the theories of networks is often rejected in the lab with a small group of people. So because of the gap in terms of the scale, group size, Fred and Sanjeev and I wondered whether the findings in the laboratory experiment in the literatures are actually valid in the large group. So these are the kind of the main motivation of our studies. And this leads us to develop the new experimental platforms in which actually we can learn the large scale up to 100 subjects so far, learn the network formation experiment. And there are several key features of the platform that we have been utilized so far. And the first one is we can actually visualize the evolution of networks in real time so that the subject can observe either entire network structure or the local information of the networks visually. The second feature of the platform is people can also make the interactive choices in real time, in continuous time, and also they can make asynchronous choices. And also the platform allows us to very wide range of information on network structure and also the payoff information. And finally, this platform can accommodate the different linking protocols that have been studied in the theory of networks. For example, like we run the experiment with a one-sided linking, and also we'll run the experiment with a two-sided linking. These are all the features that we incorporate in the platform by conducting the experiments. So we are still doing more research on this platform, and hopefully this platform will be available by the autumn this year. And then we can probably add more features by doing a research. Yes. So in this talk, I will present 3 sets of experiments conducted using these novel platforms. And the first one we call a linking game experiment. This is just an experiment about the simple game of linking, mainly based on the theoretical work of Bala and Goyal 2000 econometric paper. The second experiment is connectors and influencers experiment, and this is a linking game experiment in addition with assorted activity. And this assorted activity has the features of provision of the local public goods. And this experiment is based on the theoretical work by Gagliotti and Goyal 2010 in American Economic Review. And finally, the third one is a brokerage and the market power experiment. And we studied the setting of network formation in the trading environment. And the key issue here is how people can obtain the brokerage rent in the networks. So before I give you some details of the experimental platform and also introduce each of these three experiments, let me summarize the main experimental findings that we have throughout these three projects. The first one is that in all the experiments, we observed that the subject create a very sparse network, suggesting that the people are economizing on cost of linking. But sometimes, even if the networks are sparse, sometimes people create very unequal, highly centralized network. Other times, they create very equal network with long cycles and the long distance, multiple cycles and long distances. Regarding efficiency, in most of cases, we observe the level of efficiency very close to the level of efficiency achieved by the best equilibrium network structure. And then third one, we also observe the network connection is highly connected to the inequality of the payoffs that subject earned in the experiment. Sometimes the highly connected individual earn very large payoffs. In other times, these hubs earn much less than the rest of the individual in the networks. Finally, obviously, since we are studying the large-scale experiment, we vary the group size, called the scale, but we also vary other dimensions of the environment, including information about others' payoff, and also the pricing protocols in the intermediation problems. And these other features of environment actually interacts with the scale in a powerful way. And the main interaction is that in the large group, people tend to compete very fiercely to become the hub by making a very large amount of investment. But this pattern particularly interacts with how much information we present to the subject, and also what kind of pricing protocol they face in the environment. So now let me move on to some more details about the experimental platforms. So the first one is about the network visualizations. So in the literature, since most of the experiment is in the small scale, when they run the experiment, they fix the node in the network and then they present the connections, which is you can see in the fixed visualization with the 20 people on the left-hand side of the screen. These are the kind of the typical way of presenting the networks. But as you can see that, if the group size increase, even with these 20 people, when the people are forming a link and the networks evolve, sometimes it is very difficult to understand the exact structure of the network, as you can see here. What we do in our experimental platform is we actually adopt the adaptive visualization tool by using the force-directed algorithm that has been well studied well developed in the network science literature. And by applying these adaptive visualization tools, we can actually present exactly the same network you see on the left-hand side of screens visually on the right-hand side. And you can see more clearly what the network structure is. These are the kind of the network visualization tool that we use. So by offering the better visualizations of the networks and also help the subject understand the network structure, this actually can reduce any cognitive demands or the complexity in terms of cognition, understanding the network structure. We actually provide a better environment to test the economic theory. The second feature is actually the making the linking choices and also any choices about the associated activity in our platform is very easy to make. So for example, this is one of the screen of the, this is a sample screen from one of the experiments that we have been conducted. So people can simply clicking any node, the individual can form a link if there is no link before. Or for those who are connected, if you want to delete the link, you can simply double click that node. Then you can also delete it. And also in terms of the effort choices, we can actually use a slider bar, as you can see on top of the screen. And these all linking choices and also the choices of the effort can be done in near time in an asynchronous manner, so that you can make a decision whenever you want to do. And also the program is constantly updating in near time once other people make decisions. By doing that, actually, we believe that our choices of the asynchronous choices and also the continuous time can facilitate the learning and the better convergence. And this is particularly important because sometimes we want to compare the outcome from the small scale to the large scale, because in the large scale, there are more interaction and more information. So you may need a longer or larger opportunities of the learnings and also the convergence. Third one is about the information. So let me first talk about the network information. So in one setting, if you want to present the entire network, you can actually, in the subject screen, you can show the entire network structure as you can see it. If you can see the green color, the arrows at the bottom left-hand side of the screen. This one can actually either move the networks, and also on the right-hand side bottom, there is enlarge or the small button, so that actually you can actually, if you want to highlight some area, that you can enlarge it, or if you can make it small, you can also reduce it by clicking the button. If you want to show only the local network, for example, in this network, the network is only presented within the distance 2 from you. And all other people outside the distance 2 is actually placed on the right-hand side of the screen. So you can choose, our experiment is quite flexible about the level of this information about the local networks. Regarding the payoffs, in every network, in every experiment, people see their own performances. But if you want to show other players' performances, either you can directly show it with a numeric number, or you can actually use the color code, as you can see here, so that the green color means the higher payoff and the red color means the lower payoff. and then you can actually see others' performances by simply looking at this color. Or you can actually, we can actually show the payoffs by the numbers inside the circle. So there is a number px, this is the player's identity, and the number below it, this is the payoff informations of the other players. Finally, our experimental platform can accommodate the different protocols of the linkings, and we have been conducting experiments with one-sided linking, and one-sided linking is actually it's quite straightforward. If you initiate the link, then there is a link created. If the other guys initiate the link, then also the link created with arrows toward me, as you can see here. About the two-sided linkings, under this protocol, the link is only created both of you, or both the pair of the individual actually agree on creating the link. And this is actually the situation of the reciprocated links. But sometimes we may want to show whether someone made a link proposal that I haven't been reciprocated, or I made a link proposal that has not been reciprocated by that player. And we adopt the use of the different shapes of the nodes to represent these different types of the link proposals, as you can see it here. And under the two-sided protocol, for example, if you look at on the left-hand side of the screen, this is a one-time moment of the games. And then this node with arrow me is the U. And you can, at this time, you can observe that the P3 and P4 and P2 are the triangle shape, which means that this guy made a link proposal to me. At this moment, if I accept their link proposal, then we move to the right-hand side of the screen, and then we create the link. And also, in addition to that, I also made a link proposal to the player 6, so that guy has a square shape. So these are kind of the protocol that we adopted in our experiment. I later will tell you more about the detail of the experiments with the two-sided linking protocols. So these are all the details of the key features of the experimental platform. Do you have any questions? If I move on to the detail, okay, very good. So now let me first introduce you the first experiment, the linking games. And it's based on the Sanjeev's work in 2000. And individual, basically, only decision is forming a link with any individual in the populations. And the linking gives access to the neighbors' informations, and also the information of neighbors and etc. with the decays. And exact formula is, as you can see here, individual I payoff is the if I form a link, then I can access to the individuals of the informations, which is denoted by the V, but it's actually decayed with a distance. And also, once I connect to someone, I can also have an access through that guy's neighbor's information, and also neighbor's information as well. So the first two components is about the benefit of the linking. And then the last one, on the right-hand side of the equation, is shows the cost of linking, and the K is the constant marginal cost of linking. So these are the kind of the basic setting of the problems. And the key prediction of this model is that empty and star networks are both equilibrium. But the star network is an efficient one under certain parameter range, or certain range of the parameter, and also under the parameter values of our experiment. But the star network is efficient, but it's very produce highly unequal outcomes, which means that the hub earns more than the spokes, the rest of the individual. And the structure of the star network is like this. So there is a P1 hub, and everybody is connecting to this guy. And the reason why everybody is connecting to this guy is that the spoke can have an access to the hub's value, but also the values of all the rest of the people through the hubs. So these are the kind of the idea. Given the coincidence of the star network as the efficient network and also the equilibrium network, existing experimental work try to search for the evidence of the emergence of the star network in the small groups with a simultaneous choice experiment. And for example, like Folk and Kosfeld and the Goyal tour, they all found that the subject failed to converge to the star network in the small groups. So we will basically try to see what we found in our the features of our experimental platform. We can conduct a large scale, and also we can actually depart from the experimental literature by conducting the continuous time experiment. The parameter value that we use in the experiment, and also we have 3 treatments here in terms of the group size. We have a small group, n equal to 10, and then we have 2 large group, n equal to 50, and also n equal to 100. So when we increase the group size, actually the value of cost is very critical in forming the economic incentive in this experiment. So we basically adjust the cost of linkings by making the n divided by k constant as a half, as you can see. And in this way, the incentives are comparable in the sense that in the equilibrium network, the star network, the hub earns roughly about 50% more than the spokes in the all group size, regardless of the group size. So these are the kind of the split of the parameter selection in our experiment. And there is other details. So let me just briefly go over this other detail, which will be repeated in the other 2 experiments. And in the other 2 experiments, I won't explain these details. So experiment was run in the Linux lab in the University of Valencia in Spain. And each group plays 6 rounds of the games, either linking game or the linking and effort games or trading games in 6 minutes. So these features are all common in across all 3 experiments. The first round was a practice round, meaning that whatever subject make, there is no consequences of the earnings. Among the last 5 minutes, among the last 5 rounds, the first minute was a trial, meaning that only the last 5 minutes are the payoff relevant to the subject. And this information was public to subject. When they played the 6th round of the game, we actually fixed the groups so that there might be some concerns about the repeated games. We actually randomly reallocate the identity of the nodes in the network across different rounds so that we try to mitigate any concerns about the repeated games. And in this first experiment, we have in total 640 subjects. So now let me before I show you the data analysis of the experiment, the analysis of experimental data, let me show you some snapshot of what we observe in a particular group. But these are the kind of the representative of the outcomes in other group as well. So these are the kind of the dynamics that we can see in the small group, 10 people. At the beginning, there is lots of the kind of the activities of the forming a link among the individual, and then in the middle of the game, at the minute 3, we often observe this kind of the network you see on the left-hand side of the screen. But by the end of the game, the star-like structure emerges even in the small group of the networks, small group size. When you look at the groups in the larger groups, like n equal to 100, we often observe at the very beginning many activities of the linking. Then these are the kind of the typical snapshot that we observe in the network. So for example, at the minute 3 on the left-hand side, there is one guy in the red color emerge as a hub by attracting many links, as well as that guy is also forming many links to the other guys. Here, the blue incoming links are the actually links created by the other player to that guy. This the links in red color outgoing from the hub is actually the links created by the hub. So at the minute 3, this guy not only attract many links, but also creating many links, as you can see. In one sense, this one is actually can be interpreted as that this guy sort of making lots of linking investments to become the hub until the middle of the games. However, toward the end of the game, as you can see on the right-hand side of the screen, this guy remained to be the hub, but actually delete all the link that he created. This is kind of the common pattern that we observe across the different groups in the n equal to 100. So given that, now I'm going to show you more systematically about the main features of the data from this network, this experiment. So across the 3 experiments, we're going to actually conduct the same structure of the data analysis. So I'm going to first lay out what kind of structure we're going to use for each experiment. And then in the later experiment, I'm not going to show this one. So in every experiment, we start with a network structure. What kind of network is emerging? For that, we look at the sparseness of the networks, and also the inequality of the linkings, and also the closeness of the networks, and also one of our main interests is who becomes the hub, and then we want to see whether hub status is stable over time. So once one guy emerges as a hub, that guy remains to be the hub throughout the game. And also we see the other guy's activity as well. Now the second feature is the level of efficiency. In order to evaluate the efficiency, we observe the total payoff at any moment of the time relative to the total payoff achieved by the best equilibrium outcomes. And then finally, we'll also look at the behavior and also the inequality. When you look at the behavior, we are interested in contrasting between highly connected individual and the less connected individual, and see which one actually performs better. So in that sense, we will look at whether network connection, how the network connection is connected to the inequality of the payoffs. So in the first experiment, let me start with the network structure. So let me first start with the sparseness of the network structure, as you can see on the left-hand side of the screen. And this is the time series of the Integree, which is the number of links you receive during the games. The average person receive. As you can see that n equal to 10 in the small group, people on average get just one link. In the large group, it initially starts with about 2, but it falls down to close to 1. So in this sense, we can actually conclude that in all group size, in the end, people actually receive very few links. In that sense, create very sparse networks. On the right-hand side, this is showing the linking inequality by drawing the Lorentz curve and also Gini coefficient. I assume that you sort of remember well how the Gini coefficient is computed and how Lorentz curve is drawn. But if you look at this number called G in the legend, this one is the Gini coefficient. As you can see that in all 3 group size, the Gini coefficient is quite high, and we don't see clear monotonic patterns of the Gini coefficient by increasing the group size. So we can more or less conclude that even in the small groups, networks are highly unequal. Now, about in terms of closeness, we look at the distance in the largest component, and the average distance is either 2 or 3, and also the closeness centrality is about between 0.7 and 0.8 in all the group size. This is actually the closeness centrality relative to the star network. Now, you might ask question, what this number means in terms of closeness centrality. So in order to give you some ideas about how you interpret this, we can actually run the simulations of computing the closeness centrality for scale-free networks of Bala-Albert, for example, or Adolphs-Rennie's random network. We can also compute the closeness centrality, and you can see that this closeness centrality of these 2 representative network formation model in the literature report quite low closeness centrality compared to what we observe in the experiment. So in that sense, we sort of conclude that the network is quite centralized with a small average distance. Finally, as you can see that on the left-hand side, this is the empirical likelihood of the people who becomes a hub within the 10-second time intervals at the particular time moment, whether that guy remain to be the hub in the next time interval of 10 seconds. And as you can see that initially in the first 1 minute, you can see the dotted horizontal line. That's the first 1 minute practice period times. And this the hubs are quite unstable at the very beginning, but from the beginning of the real games, like at the end of the first minute, in all 3 experiments, this hub in one time interval remain to be the hub with 80% of time in the next time interval of 10 seconds. And this stability increases over time, as you can see. On the figure on the right-hand side is actually the average number of decisions that people are making in every time interval. And actually it's steadily decreasing, so that somehow this suggests that the network structures are sort of stabilized over time. So in that sense, we can actually make a conclusion that the network structure in this linking game is, we observe subject create the sparse and unequal and small average distance networks. That's kind of the overall summary from this experiment. Second is about the efficiency, and this is actually across 3 different group size. We are comparing the total payoffs relative to the payoffs achieved by the best equilibriums. And as you can see that the efficiency ratio is higher in the small group than in the large group throughout all period or minute. However, toward the end, it's actually rapidly increasing at the very beginning of the first minute and then steadily increasing over time. So in this sense, we conclude that the overall group size level of efficiency is high. However, the efficiency decreases in group size. Finally, about the behavior inequality, for this actually we classify the subject into 3 different types. The first one is at every time moment, we define the individual with highest link as the highest number of the link is the most connected. And second largest number of the link we call the second most connected, and the last of individual as others. And this is a small group, as you can see that. The graph on the left is the time series of the outdegrees, like the number of links you created across different 3 subject groups. And as you can see that there are no clear differences between these 3 types. However, the most connected individual actually receiving a more link so that the payoffs are higher, as you can see, slightly higher. However, in the large group, n equal to 50, this is n equal to 50, the most connected and the second most connected individual is actually forming a much more link than the rest of individual. And these 2 guys particularly forming many links at the early stage of the games. But once the most connected guy becomes a hub, this guy is steadily reducing the link. But then this has a clear mirror image payoff consequences, as you can see on the right-hand side of the screen. And for the most connected and second most connected individual, this guy is actually losing a lot of money at the very beginning, at the early stage of the game, in the hope for the larger payoff at the later stage of the game, as you can see from this red line. The same pattern for the n equal to 100. And if we just check the correlation of the payoffs between highly connected and the less connected, we can actually learn simple OLS regression, as you can see here. And the omitted variable is the rest of individual. And we can actually look at the median payoff of the most connected and the second most connected. As you can see that n equal to 50 and n equal to 100 compared to the rest of individual, most connected and second most connected perform significantly worse than the rest of individual. But that's not the case in n equal to 10. So in this sense, we conclude that in the small group, higher degree is associated with a higher payoff. However, in the large group, because of intense competition to become the hub, higher degree is associated with the lower payoffs. Okay. So these are the kind of the presentation of the first experiment. Do you have any questions? Now let me move on to the second experiment then. So this is a connectors and influencer experiment, and this is simply just adding the activities in addition to the linkings. And this is based on the Sanjeev's another paper with Andrea Gagliotti. And the main sort of ingredients of the model is actually individual choose costly effort and also the form costly links. And the linking gives access to efforts of the target person that you connect, but also the efforts of her neighbors. So there is a direct benefit from linking, but also there is indirect benefit from the target neighbors. In this sense, in this environment, your own effort is actually a strategic substitute of the efforts of the others. So if you making a link to the someone with a lot of effort, then you don't have an incentive to maintain a high effort. So you can actually reduce the effort. So these are the kind of again, the similar type of the benefit functions with inside the function f, there is my own effort, and this is my neighbor's effort, and this is my neighbor's effort with some decay factor. Okay. And the second component on the right-hand side, this is the cost of effort, and the C is the constant marginal cost of effort. And the last component is the cost of linking, and the K is again the constant marginal cost of linking. And the prediction of the theory is basically the law of the few, in the sense that there is a society has the specialization in efforts and linking, meaning that a few individual becomes the hub, and then that guy, and then also the effort of distribution is the highly constrained on a few individuals. And in terms of network structure, the equilibrium network is a peripheral sponsored network. However, the effort configurations are the two different types, either pure influencer and then pure connector. Pure influencer means that the hub's making all the effort, whereas pure connector is the hub making a zero effort. These are the kind of network structure. On the right-hand side, on the left-hand side, you can see the pure influencer network structure. On the right-hand side, you see the pure connector network. We have a particular selection of the parameter values, and given the selections, under the equilibrium outcomes, the pure influencer, we observe very little inequality of payoff, meaning the hub and spokes are similar because hub has more connection, but hubs are making all the effort. In the pure connector, hubs actually attract lots of link. At the same time, he makes a zero effort, so that hubs earn much more than the spoke. In that sense, there is a large inequality of the payoffs. In our experiment, we have a 3 group size, and also we have a 2 information structure. In the baseline, we only present subjects, we only give a feedback about the subject's own performance. In the payoff information setting, we also give the information about other players' payoffs. In total, we have 1,064 subjects, and experiments was run at the Linux. Now, let me show you some snapshot of the dynamics in the baseline in the large group, and then also I'll show you a snapshot of the payoff information in the large group. So this is a baseline where people can only observe their own performance. Now, at the first 1 minute, already P26 emerged as a hub. Now, inside this circle, there is a number 20. This number 20 means that this guy's effort. And the effort is ranging between 0 and 20. So in the 20 is a maximum effort level. And this guy is making a maximum effort, and then they create lots of links. They attract lots of links, as you can see here. And they, even at the first 1 minute, at the end of the first 1 minute, he already becomes a hub. But then there is a bunch of other guys also making a 20 maximum effort. And one of them is actually P97, as you can see here. Now, what happens in the minute 3? At the minute 3, this P26, who was hub at the first 1 minute, is actually reducing her effort from 20 to 3 by minute 3. Whereas this P97 actually maintaining the maximum effort until the minute 3. Because this guy is choosing higher effort, some individuals are actually forming a link to this individual. So there you can see the emergence of the another hub in this setting. Now at the minute 5, this P97, who again maintained the effort 20, is actually replaced this P26, who choose a very low effort by the time. And then at minute 6, this P97, once he replaced the other guy's hub status, he remained to be the hub at the end of the games. So these are kind of the typical dynamics that we see in the baseline large group. What about in the payoff information in the large group? We again, at the first 1 minute, we again observe one guy emerging as a hub, relatively high effort. But this guy, at the minute 3, start to reduce the effort. But we don't see any other people is actually competing this guy with seriously, with a maximum effort or the very high effort. And also the start to be emerging hub. At minute 5, this guy remained to be the hub, but making a 0 effort without facing any serious competitions. And then at the minute 6, this guy remained to be the hub, and then but making a 0 effort. And this is a kind of pure connector outcome, as you can see. So key points from the snapshot is that actually we observe very specialization, linking, and effort. In the baseline treatment, we observe emergence of pure influence outcome. In the payoff information treatment, we observe the emergence of the pure connector outcomes in the large group. That's what we observe. Now, we're going to see more systematically by following the same steps of the data analysis as in the first experiment. Okay. Now, let me start with the network structure. Again, here I will do, on the left-hand side, this is baseline. On the right-hand side is payoff information. Within each panel, there is a 3 group size. The in-degree is around 1, so it's very sparse network. About the linking inequality, both baseline and the payoff information in every network size, we observe very highly unequal outcomes, unequal linking outcomes. However, the one thing that we can note is in the baseline treatment, actually group size, when the group size increase, this Gini coefficient increase, meaning that in the baseline treatment, the inequality of the linking is actually increased in the group size. Whereas in the baseline, we don't see such a pattern very clearly. About the closeness, average distance is again the small, either 2 or 3, in both baseline and the payoff informations. Closure centrality is again, is it growing, and then at the end, toward the end of the game, it's about between the 0.7 and the 0.8. Stability is again, it's a relatively high, so that once hub emerges, that guy is very likely to be the hub in the next time interval of 10 seconds. And again, we observe the declining pattern of the number of activity, in terms of the number of linking choices. So all this, we can conclude that the network structure, subject create a sparse and unequal small average distance network post group size, across different group size and across different information treatment. However, linking inequality increase in group size in the baseline, but not in the payoff information treatment. Now about the efficiency, here the best Nash equilibrium network structure is a star network. So everything is normalized by the star network, and then you can see that in all group size, the level of efficiency is very close to the efficiency achieved in the star network. However, in the baseline treatment, n equal to 100, the level of efficiency is actually higher than the star network. And then the reason is that the hubs are making an excessive investment, and that actually creates a spillover effect to the other individual payoffs, so that it overall increases the total payoff. Now the summary is that efficiency level is quite high, and group size lead to higher, larger payoff in the baseline tree. Finally, about the behavior and the payoff, we look at the effort as the main behavior. And I will start with a small group. So this is the top panels are the figures from the baseline, group size 8, and the bottom is a payoff information, group size 8. And on the left-hand side, this is the dynamics of the effort. And on the right-hand side, this is the dynamics of the median payoffs. As you can see that most connected individuals are actually making more effort, but it's around 9. And that's actually the equilibrium effort level in theory. And we don't see, there is some differences between the second most connected, but these most connected individuals' efforts are not excessive in the sense that it doesn't reach to the maximum effort level 20. So that the payoffs are, of all these 3 individuals, very close to each other, although the most connected individual earns slightly more. And the patterns are quite similar between the payoff information and the baseline information treatment in the small group. If you look at the large group, the patterns are quite different for the most connected individual. If you look at on the left-hand side, top panel, these are the baseline group size 50, the 2 most connected individuals making a very excessive effort, whereas the bottom left-hand side panel, payoff, under the payoff informations, effort levels are quite low. And it has a payoff consequences on, as you can see on the right-hand side. And the similar patterns on the n equal to 100. And if you run the simple ONS regressions about this, and also the median regressions, what you can see here is that in the baseline, which is the first 3 columns, moving from the small group to large group, you can see that the more connected individuals are actually performing worse than the rest of individuals. Whereas payoff informations, when you move from the small group to large group, the most connected individual perform actually better than the rest of individual, because in the payoff information treatment, most connected individual actually making a moderate level of effort or very low effort, because as you can see, the pure connect outcome. However, in the baseline treatment, highly connected individual face intense competition and make lots of investment and losing money. And that's what you can see here. So this is a summary, and then this is kind of the end of this second experiment. Do you have any questions? Okay, so let me move on to the third experiment about the brokerage and the market power. And the basic question that we have is that in the real life, we observe the emergence of dominant intermediaries like Amazon, Walmart, Google in the real market. And we try to understand, there may be many different mechanisms that make the emergence of the dominant intermediaries. We want to study this in terms of the scale and in terms of the pricing protocol. The network perspective that we have here is that thinking about the 2 individuals, for example, P1 and P3 on the left-hand side of figures, these are the directly connected, so that they can actually directly connect trade. But if you look at the player P1 and P6 on the right-hand side of the network, there is no direct link, so that they cannot make a direct trade. However, there is an indirect path between them. There is a trading path between them, so that they can actually use this trading path to trade. But by using this trading path, they are using the intermediary services. Now we consider 2 different the pricing protocol. The first one is a criticality-based pricing, meaning that thinking about the player 7 and the player 2 here in the figure, they want to make a trade, but there is no direct trade. So they have to go through it. But there are 3 different paths. So they can use whichever they want to use, but there are 2 players, P1 and me, are the kind of the gatekeeper for these intermediations. And we call these guys the critical traders. And this P7 and P2 can make a trade, but they have to share the value of the trading, surplus of trading, with this critical player. They don't need to pay any rent for the non-critical intermediary. So this is we call the criticality-based pricing. About the betweenness-based pricing, again, let's think about the player 2 and then player 7. And again, there are 3 different paths. And this player can use the shortest trading path, which is either this one or this one. But then they have to pay the surplus, some of the surplus to everyone on the trading path. And we call this is a betweenness-based pricing. Now we can make some theoretical predictions based on the criticality pricing and then the betweenness pricing. But the key idea is that the circle network is the pairwise stable network under criticality, but not in the betweenness pricing. However, the hub spokes networks are the pairwise stable network under both pricings. So I have 2 more minutes, right? Okay. So in the experimental design, we have 2 pricing protocols and 3 group size, as you can see. And in total, we have 1,280 subjects. Now, again, under the value of the experiment, actually, you can think about what kind of 2 different types of network. One is a hub-spoke network and another is a cycle network. The hub-spoke network is an efficient network under our selection of the parameter value, but very unequal. However, cycle network is very almost efficient and also very equal outcomes. Now, let me show you a snapshot of some criticality pricing in the large group and snapshot of the betweenness pricing in the large group. So this is criticality at the minute 1. You can see that the efficiency level is 61% and inequality is quite already, inequality is about 3.1. Now in the 3 minutes, efficiency increase by the network becomes more sparse. Inequality, there is a little change. At the minute 3, efficiency keep increasing and the inequality is about this size. However, in the betweenness, initially efficiency level is very low. In the minute 3, one guy starts to emerge as a kind of hub. In the minute 6, that guy emerges as a hub and achieve very high efficiency. And inequality, which is measured by the ratio between the max payoff to the median payoff, and it's quite high. Now, the network structure, in both settings, the network is very scarce. In the betweenness pricing, the distance is smaller, but the closeness centrality is the network is more centralized on the betweenness, but not criticality. The top broker is quite stable in the large group, in the betweenness, but not in the criticality. So that we sort of make a conclusion that in terms of network structure, pricing protocol plays an important role in a sense that under both pricing protocol, networks are sparse. However, on the criticality, it's very spread out network. However, on the betweenness, this is very unequal small average distance networks. Now, I think time already passed, so let me show you the inequality and then I can close. Okay. So let me only show you the inequality about the brokerage rent. On the criticality, this is a distribution of average per individual payoffs, n equal to 10, 50, 100, and this is between, the top panel is about the criticality, and the bottom is a betweenness. As you can see that very few individuals under the betweenness achieve very large amount of the brokerage rent. And this one is actually lead to that this under the betweenness treatment, the people receiving lots of link achieve very high payoff, and then this is constantly increasing over time. However, we don't observe such a pattern under criticality, as you can see. So that overall, we conclude that pricing protocol plays an important role of generating the inequality and also shape the subject's behavior a lot. So let me conclude. So we developed a novel platform for large-scale continuous time experiment, and we apply this platform to the 3 different types of the network formation problems. And now we are extending the use of this platform to the problem of the learning in social networks. Thank you.